Now we want to look at inverse functions and their derivatives. There is a relationship between the derivatives of a function and its inverse. Now before we actually get into that relationship, let's just do a little bit of review about inverse functions. The first thing you learned before you learned about inverse functions was about one-to-one functions. A one-to-one function is a function a function is one-to-one if f of x sub 1 does not equal f of x sub 2 whenever x sub 1 doesn't equal x sub 2 in its domain. What that means is that different x values will have different y values. Now, in order to be a function, you could have two x's with the same y. You just couldn't have one y with one x with two different y values. To be one-to-one is a little bit more specific. Each x value has to have a specific, unique y value. Now to test whether or not functions are one-to-one, we can use a graph and the horizontal line test. Remember, a vertical line test told us whether or not a function was, or a graph was a function. The horizontal line test tells us whether or not that graph is going to be one-to-one. If a horizontal line crosses the graph only once at each spot, then it is one-to-one. Now the two graphs at the top are both one-to-one. No matter where we draw a horizontal line through these graphs, it will never cross more than once. They are one-to-one. The two at the bottom are not one-to-one. If we draw a horizontal line through these graphs, it will cross twice. What that means, like for y equals x squared, is that at -1 and at +1 you have the same y values. Now the reason that this works is when one-to-one functions tell us that the inverse of its equation is also going to be a function. And when we find inverses, we switch our x's and our y's. If we switch the x's and y's on this graph, we would have a graph that was a parabola on its side, which of course would not be a function. It would fail the vertical line test. So when we switched our x's and our y's, we would have two different y values for a given x. If we switch the x's and y's here, we would have an x of 0.5 that had two different y values, one at pi over 6 and one at 5 pi over 6. So if f is a one-to-one function, an inverse function is defined using this notation. This is read f inverse of a. And f inverse of a is b if f of b is a. And so basically we are just switching the x and y values. Now here is an example of functions that are inverses of each other. We have this y equals the square root of x, and we have y equals x squared for x greater than or equal to 0. Okay, and that is important because we looked at the last, a couple of slides back and we saw y equals x squared was not one-to-one. So this is restricted. What happens here is for any point on our graph, x, y, for the other function, we will just switch the x's and the y's. Notice that the graphs are symmetrical about the line y equals x. And anytime that we have inverses and we look at their graphs, they will be symmetrical about the line y equals x, which means basically I could fold along this line y equals x and the left and right hand sides would match up. Now here are a couple more examples of graphs that are inverses of each other. And if it's an inverse, if I have the point AB on this graph, I will have the point BA on this graph. The x's and y's switch places. When I look at the slope of this tangent line and the slope of this tangent line, there is a relationship between the two. The slopes of the tangent lines are going to be reciprocals of each other. And that gives us the derivative rule for inverses, which basically says that if f has an interval I as domain and f prime of x exists and is never 0 on I, then f inverse is differentiable at every point in its domain. The value f inverse, the derivative of f inverse at a point B in the domain of f inverse is a reciprocal of the value of f prime at the point A. Now let's talk about what that means. For example, if I have these two graphs from before, I can have the point 2, 4. On this graph, I would have the point 4, 2. Okay, we just switch the x's and y's to get the points on opposite graphs. Now let's think about this y equals x squared, and let's think about its derivative. That's really easy to take. We just pull the 2 out to the front, and its derivative is 2x. So if I'm looking at the point 2, 4 along this graph, then the slope at the point 2, 4, which we can denote this way, the derivative when x equals 2 will be 2 times 2, or 4. So if the slope is 4 here at 2, 4, when I come over here to this graph and I find the slope at 4, 2, it's going to be its reciprocal, which is 1/4. Now just to show that that is true, if we take this, and remember that this is the same as y equals 1/2 x, we need to think about root functions as power functions in order to be able to apply the power rule. That would be 1/2 x to the negative 1/2. And x to the negative 1/2, of course, is the square root of x in the denominator. And so y prime here, when x is 4, would be 1 divided by 2, square root of 4, or 1 divided by 2 times 2, which is 1/4. So if at 2, 4 you have a tangent of 4, then on its inverse at 4, 2, you will have a tangent that has a slope of 1/4. Now let's look at another example. We have this graph in blue, which is y equals x cubed minus 2. Notice I'm not given a formula for the graph in yellow, which is its inverse. Now I could find that by switching my x's and y's and solving for y. But I don't have to do that. If I take the point 2, 6 on this graph and I find its slope, then the slope at 6, 2 will just be the reciprocal slope. So if I take and find the derivative of this function, I bring my 3 to the front, subtract 1 from the exponent, 3x squared. The derivative of negative 2 is 0. So the derivative of the function f is 3x squared. Now if I find the derivative at x equals 2 here, then that will be 3 times 2 squared. 2 squared is 4, so I have 3 times 4, or 12. Now without ever finding the equation of the inverse, I can tell you that if the slope is 12 at 2, 6, then at 6, 2, the slope is going to be its reciprocal, which is 1/12.